Hey everybody, part 2 of 5.3, which makes this the final video of AP Calculus BC. A little bittersweet, but just like the huge has been in this Unit 5, part 2 here is going to focus on the calculus stuff with these polar functions. So here we go. Actually, first, please make sure you stick around all the way through to the end, because even after I get done with all of like the notes that you see on your handout, I'm gonna kind of skim through the homework and fill you in on any like hints or like any inside scoops there might be when it comes to like some of the homework problems. So make sure you watch all the way to the end. So here we go. We start off with slopes of polar curves. That's calculus. Oh, and what looks like a typo ticks me off. The polar. I think that the polar rectangular. I don't think we need two polars. So the polar rectangular conversion formulas enable us to write x and y as functions of theta, like parametrically. So remember in like part 1, we learned how we can take like polar equations and rewrite them, with like a parametric type vibe. And that's going to help us here because let's face it, slope is rise over run. I don't know if we can do slope with like r and theta. Like I think we have to write it as x and y, right? Because it's got to be dy dx. And so we're going to do that whole parametric thing, right? And basically our formula for dy dx is going to end up being dy d theta over dx d theta. And I don't think it's too difficult to see how that works, at least like algebraically, how dy d theta over dx d theta is equivalent with dy dx for slope. So here we go, an example. Find the slope of the rose curve, r equals 2 sin of 3 theta, at the point where theta equals pi over 6. And use it to find the equation of the tangent line. Classic. But I don't think there's going to be any homework problems that require you to do like this last part. Just kind of like the slope at certain theta values, if I'm not mistaken. So anyway, to do this, we first need to define x and y like using like parametric equations. And remember from part 1, all you need to do is to take this 2 sine of 3 theta and tack on a cosine of theta, and that's what x equals. Similarly, all you gotta do is tack on a sine of theta to that 2 sine of 3 theta, and that's what y equals. And so then we look to do our dy dx, which is dy d theta, which is the derivative of this with respect to theta, just like this is you take the derivative of this with respect to theta, and that's what dx d theta is. Now, when you look at taking the derivative of either one of these, I hope it occurs to you pretty quickly how you're supposed to do it. Like think back to, with Mrs. Clute, okay? How are you going to take the derivatives? Wouldn't you need, oh goodness gracious, wouldn't you need like a product rule? So remember, first times the derivative of the second plus the second times the derivative of the first, which required a chain rule. Don't forget about your chain rule when it applies, okay? When it pops up. So same with the dx d theta. It's gonna involve a chain rule. Now, I suppose this cleans up maybe a little bit. I don't know. Like, it doesn't really matter because the bottom line is that you're just going to be plugging in pi over 6, which is the same as 30 degrees, okay? Now, you can use, I mean, I'm going to take the few seconds to go like remember like all this stuff, I mean, you can maybe make use of, or maybe you're good enough to do this in your head, like what the cosine of 30 degrees is, or negative sine of 30 degrees, or I mean, what 3 times theta would be 90, so what's the cosine of 90? What's the sine of 90? Or you can just throw all this into your calculator. Just make sure you're in the proper mode, but I mean, like, the bottom line is the final answer is negative square root of 3. Looks like what I would probably do is I would plug 30 degrees or pi over 6 into all of this and just throw all that into your calculator kind of at one time, and it looks like we got root 3, and then separately crunch all that out on your calculator using 30 degrees or whatever, and you get negative 1, and so like your final slope is negative root 3. Now the rest of this, we have to use it to find the equation of a tangent line. Well, to find the equation of a line, what I always look for is, the slope, which it looks like we have it, and then we just need like any random point. So maybe we can use theta equals pi over 6, and that would get us both an x and a y, I think. Yeah. So just, you can get an xy combination just by plugging in, theta equals pi over 6, for example, and we end up with x equaling that and y equaling that, and so there's a point, and so you put your slope together with a point, and it's like you're back in algebra 1, and then yada yada yada, right? And this would continue to evolve until, I guess, it was in like slope-intercept form or whatever. But again, I don't think this is going to pop up on your homework, but you should write it down for your notes, I guess, And now we get into area enclosed by polar curves. Woo, here we go. First, a little illustration of how in the past, when you took Calc AB and you were finding area under a curve, with like a Cartesian rectangular type equation, you were adding up all of these rectangles, like infinitely thin rectangles, you know what I mean? Here it's going to be kind of like this. A small change in x produces a regular strip of area, but with the polar stuff, a small change in theta produces a thin sector of area. Okay? So, I mean, yeah, we're going to be doing like delta theta and sort of like accumulating area like this. It's might be a little bit heavy at first to wrap your brain around, but some of the good news is that we're just going to end up with, if we kind of start a little discussion from from this concept, ultimately we're going to end up with this formula. We're going to integrate from wherever to wherever, alpha to beta, whatever theta values make sense. Okay, can I even make a, let's say we were finding, the area of the entire, enclosed by the axes and this curve, just in the first quadrant. You'd be going from theta equals 0 to theta equals pi over 2. So you're doing from theta 1 to theta 2, or we could accumulate this area from pi over 6 to pi over 2. You know what I mean? That's how it's going to kind of play out with these limits of integration. And then, like I said already, the rest of this formula just kind of goes like this: 1/2, and then your function f of theta squared d theta. All right, so in this regard, these problems are going to end up pretty simple. So let's do one or two pretty simple examples. And maybe I'll go, I don't know whether this is a better idea or not. Let me sort of first skip ahead to the end of your handout, right? Where I give you kind of a rundown of all of these different polar shapes. Okay, here are a few of the more common polar graphs and the theta intervals that can be used to produce them. So this is actually a pretty big detail to keep in mind as we move forward and as we look ahead to the homework. So you could have a typical circle, r equals 2, okay, and the interval that produces the entire circle is 0 to 2 pi, because it goes all the way around. But there are certain graphs, like this kind of circle, r equals 2 sine of theta. This circle gets produced only by using the interval from 0 to just pi. Same with a circle like that, these rose curves, this type of rose graph where there's an odd number of petals, you only go from 0 to just pi, and that would produce the entire rose curve, okay? But for these ones where there's an even number of petals, you got to go all the way from theta equals 0 to theta equals 2 pi. So I don't want to linger too much longer on this for now, but I want you to take notice of especially the ones where it only goes from 0 to pi. Most of these go from 0 to 2 pi in order to create the entire graph, but we have this is interesting with the r squared and stuff. But I don't really mind that too much. But these are called lemniscate curves. I'm not really sure how to pronounce that properly. Limacon curves, and there's all these different kinds of limacons. Cardioids and dimpled limacons and convex limacons. It's crazy. But anyway, so keep that in mind. Now this is a cardioid, and I'm going to do my best to kind of point out what type of polar graph it makes. So this is a cardioid, and this is one of the ones where to create this entire cardioid, we do got to go from 0 all the way to 2 pi. But you know, there's no tricks to this. Like, there's no surprises, there's no plot twists. You're just going to take your basic format, your formula, your setup, and, remember, f of theta, that's just going to be this. If you want to distribute the 2 here, I wouldn't blame you. I kind of have the like, that seems like a reflex to me right now, is for some reason just like distribute the 2, but whatever. That's what your f of theta is. And so you're going to go from 0 to 2 pi of 1/2, don't forget the 1/2, of that function squared d theta. And, I'm going to show you this, but all you really got to do, here is throw it into your calculator. Do like a little Math 9 action. Type all that in. Make sure you're in radians. Alrighty. And by the way, when you graph these things, like I have these graphed for you, but if you were going to graph this on your own calculator or whatever, I'm pretty sure you'd have to be in radian mode as well as polar mode, polar mode to get the r equals set up for you. But I'm pretty sure you got to be in radian mode. And I think you got to be in radian mode when you're doing like the Math 9 integrate thing. But you get, 6 pi or whatever, 6 times 3.1, you can estimate that. But I think here is like the doing it by hand way, which, whatever, you can write that down. I'm going to move on, but you can pause the video if you need to. But, you can just use your calculator in most circumstances. Then there's this, okay? This could potentially throw you for a loop. Read this over, huh? Find the area inside the smaller loop of this limacon. So, right here, this is obviously theta equals 0. So I'm sure, like, see, these polar graphs can be pretty heavy. You know what I mean? Like wrapping your brain around how this gets constructed. If you wanted to like construct a really extensive table of like theta equals 0, and then it looks like you get a radius value of 3. You know what I mean? So that point. But then, like, when theta equals like pi over 6, you probably are at this point. And then, when theta equals, I don't know, pi over 4, where would that be? Like there, I guess? Is that, I'm trying to, I guess right there, huh? Why is this messing with me? 45 degrees, about, so, there you get a certain r value for pi over 4, and you would have that dot. You eventually get to here, and it looks like you would get this point when theta equals, pi over 2, which is 90 degrees. And then I would assume, this is the point you would get when theta equals 270 or 3 pi over 2. So we kind of want, what are my theta values that resulted in, this part of it, all of these points. You know what I mean? Like we got to here, and I don't know, we just kind of kept going and stuff like that. I don't know, like, again, these things can kind of mess with your head a little bit. So here's what you're going to want to have your approach be. Like, here's the approach you're going to take. It looks like we got to here, and this was literally when your radius was 0. You know what I mean? So it's almost like we started this section like right here when the radius was 0, and then we kind of like ended this section when radius was back to equaling 0, you know. And I guess all of these would have been like negative radii, negative radiuses. So here's what you're going to do. You're going to set this equal to 0, because right there is where like we're kind of starting and ending this section. And so if you set this equal to 0, you end up with the cosine of theta equals negative 1/2. Okay? And then you can kind of use a cheat sheet or like a calculator or whatever or whatever you need to do, and you can figure out that theta to satisfy this would be 2 pi over 3 and 4 pi over 3, which is kind of wild, you know, because think about it. 2 pi over 3, that's 2/3 of pi. Where would that be? You know, it looks like, I mean, check it out. So like when you're talking about this angle, you know what I mean? It's almost like these are, you know, on this angle or this angle, or it looks like we're going from like here and then all the way to like here. You know what I mean? Where if there was positive radii, it would have kept looping out here. You know what I mean? With all these positive values. But since we're, so for example, like this angle right here had like a negative radius, and so it ended up being like one of these points right around here. You know what I'm saying? Anyway, I mean, the point is, like, you solve this equation when you set it equal to 0, only because that's where the radius was equal to here and here. And then, you know, you just kind of integrate from 2 pi over 3 to 4 pi over 3 of 1/2, the function squared, go to your calculator, and you get that. Okay? So I guess on this one, the big thing to figure out, the big hurdle to get over, was figuring out these limits of integration, you know. So like from 2 pi over 3 to 4 pi over 3, you know. Anyway, so remember examples like this. We're also going to do area between polar curves. Oh no! So here's what ends up being like the final draft of the formula. We still got the 1/2, and we're going to do like what boils down to like an outer radius, you know, like the outer function squared minus the inner function squared. Okay, so pause the video if you need to write down at the very least like this final version of our formula, and let's do an example. Okay, so find the area of the region that lies inside the circle, which is represented by r equals 1, and outside this blue cardioid. All right. So that would be that purple area. You know what I mean? So what we have to do is find this section of area. And to do that, we can kind of do like the outer. So basically from like this angle to this angle, you know, we got the circle being like the outer function and the cardioid being like the inner function. So, let me throw this in here. Let's say they wanted you to figure out, you know, the area that was shared by the circle and the cardioid. That would have been like this part right here. it wouldn't have been simple. Like this, it's going to absolutely be just, the outer function squared minus the inner function squared. But finding this piece right here, I mean, that's a little more interesting, because what would be like the outer function and then what would be like the inner function? That's a interesting question. And so try to keep this in mind, people, right? If what you were supposed to find out was this shared area, I think what you'd have to do is find this area anyway and then subtract it from the circle as a whole. So if you take like the whole circle and you subtract this chunk, what's left over is the piece that is shared by both graphs. But anyway, I digress. So it looks like we're going from negative pi over 2 to pi over 2. Like we're starting here and we're going like to positive pi over 2. But this is where I throw a pretty big wrench into our current world. If we integrated from negative pi over 2 to positive pi over 2, would that work out? I don't know. I guess, and you might want to write this down in your own words or however you want. This is kind of like a general rule of thumb with these crazy polar graphs, with all the sines and cosines. And so in general, you have to be very, very suspicious of whether or not you're actually accumulating like positive area, that's all positive area, or like if mixed into your interval you have like some negative area. It's wild. Like it's a wild world of like looking at these things and trying to wrap your brain around the fact that like, should we do like this whole chunk and just assume that it's accumulating all positive area? Should we throw some absolute value into play? Trust me, like it's a thing. It's a big thing to worry about. So one thing you can do to combat that potential like issue is like throwing in some absolute value in the proper place here and there. But I think what I'm going to do here is I'm just, especially because I'm going from like a negative angle, see, I wonder if it would have been better to kind of go from like 3 pi over, again, I hate to keep elaborating on this, but would it make sense to go from like 270 to 90, or like negative 90 to 90? I mean, maybe that would work. I mean, I don't know, but I feel like a lot more comfortable just going from 0 to 90 and then just doubling it. Like, let's find this chunk, which I feel a little bit better about, like actually working out the way I expect it to, especially like all positive stuff, and then just doubling it to equal like what all of this would be. So I mean, and once again, you can ignore all this if you want to. This is doing it by hand. Going to your calculator, you just end up with like approximately 1.215. But I hope, and look, a lot of this is going to be like kind of trial by fire as you're doing the homework, or as we do the homework together and stuff. All these different situations where, setting up, and again, a lot of it's like it's an easy formula to follow, but then again, setting up the limits of integration and using tricks like this, where like, oh, let's just go from 0 to pi over 2 and just double it. you got to be pretty crafty. You know, hey, like I said earlier, what if it was this area you had to find? You have to be a little bit crafty. You got to be clever. Um, so I already addressed. So please keep in mind, God, this is like another plot twist in things where, you know, to graph this, it's just from 0 to pi. So keep these pages in mind, all these different type of graphs. But now I want to kind of, please stick with this. I want to give you some help on the homework you're about to do. So 39 and 40 and 41 and 42, you're going to find the slope of the curve at all of these theta values. So what you're gonna find what x equals and what y equals, doing that whole parametric deal, and then you got to do that crazy dy dx formula of like what dy d theta all over dx d theta. So that gets a little bit ugly, but then people just use your calculator to plug in 0. Maybe you can do some of it in your head. I mean, plugging in 0 can be a pretty easy thing. So it's just some ugly number, like some ugly derivative work, you know, product rules and stuff like that. Now 41 and 42, look, please take advantage of how you can like literally look at the slope of like where theta equals pi over 2. I mean, spoiler alert, when theta equals pi over 2, it's obvious that your slope is 0. I mean, that is a horizontal line. That is a horizontal line. These right here in number 42, these are vertical lines at theta equals pi and at theta equals pi over 3. This is so use that to your advantage, okay? So you're probably only going to need to actually plug into for your calculator like this line and these couple of lines. Oh, and by the way, hey, I'll even save you a little bit more work. Whatever you get when you plug in pi, or 0, you might want to plug in 0, it's easier. You know, whatever you get when you plug in 0, these limacons, I can't see, I don't even know what these are by heart, but this graph is symmetrical. I mean, look, I think that's kind of common sense. Just by so whatever, you know, 2 comma 0 is, whatever that slope is, won't that just be the opposite of it? You know, the positive version of this negative version. Anyway, so kind of think a little smarter, not harder. Okay. Oh. Now this, man, again, these get heavy. I think I gave you some pretty good tips in the while we were taking notes, but I figured you can kind of graph this yourself if need be, so I left this one ungraphed. But inside the convex limacon, you know, you might want to double check whether this is going from like just 0 to pi or 0 to 2 pi. Inside the cardioid, inside, hey people, inside one petal. So these are the types of things you need to think about. We're just doing, so, I mean, what do? Do you go from like 0 to 2 pi and get the whole area and then divide by 4? Or do you think you can like figure out what this angle is and what that angle is and just literally integrate? I mean, you could set this equal to 0, I suppose. I mean, it's up to you what you think is more reliable and easier. Inside the 8 petal rows. Once again, I mean, do you just want to go from 0 to 2 pi, or, well, I guess you probably want to, because it's the entire 8 petaled rows. These suckers still kind of vex me a little bit as far as like you know, graphing it, like throwing it into like your graphing calculator and all that kind of stuff. Yeah, these are crazy. You know, we can talk about these at a later time. But here's a hint for you, okay? Number 47 might be one of those ones where you feel like you're going to need to throw some absolute value into the integral to make sure that as you go from 0 to pi or 0 to 2 pi, let's see here. I mean, yeah, as you integrate from 0 to pi, I'm just saying you might want to throw some absolute value into what you're doing, or I don't know, whatever you can find that works. But inside this 6-petaled rows, see, once again, r squared. So it's like when you graph this, and it's like, you know, positive square root of this and negative square root of that. I mean, it's crazy. And I just know with these roses, there's so much like there's like negative radii and stuff. So again, like it doesn't hurt to throw some like absolute value into your integral to make sure that you're accumulating area. I mean, what you might want to do, see, sometimes a better strategy is to like maybe just find one of, because it's very symmetrical, right? Just find one petal, right? Like maybe find the area of this petal, which you know, you might want to again double check that it's all like positive radii and stuff, but and then multiply that by 6. I mean, whatever you can do to figure it out. Dimpled limacon. Double check your intervals. Inside this loop. Okay, we kind of did that. And then you get into like these. Ooh, what's being shared by the circles? That's interesting. That is interesting. This is a juicy problem, because I mean, I'm going to tell you right now, in number 51, what's being like this chunk right here that's being shared, I don't think you can, I don't know, I don't think you can like go from like here to here and say like there's an outer function, this is in the inner function. I don't know, man. Number 51, you got to get you have to get clever, I think. You have to get really clever about how to end up with this area. You know what I mean? Yeah, I mean maybe, you know, I think I remember what I did, but I don't think I want to give that spoiler just now. 52, once again, shared. What's being shared? That's interesting. You know, would that even be outer, inner? That's interesting. Outer, inner. Ooh, I think I know what I would do. But yeah, I think for 52 you have to get like really, really clever, and it's not just that formula straight up. And so anyway, come on. Shared. See, shared by the circle and the cardioid. I warned you about that. Shared by these two cardioids. So you got to get pretty clever with 53 and 54. 55 is a little more straightforward. That's okay, just saying. And 56 inside the 4-petaled rows, but outside the circle. Okay, all right. That's doable. Anyway, I hope I gave you at least some warnings. Again, it's pretty heavy, but it's challenging in a good way. But I hope I gave you some good warnings and some good tips and stuff like that. And good luck.